Hi, I'm Mark Weitzman. Welcome back to our final video on the Feynman Heaviside fields. So we have this formula for the electric field in terms of some retarded quantities and derivatives of retarded quantities. And we want to get it into this Feynman Heaviside formula. Now the key thing to notice is the Feynman Heaviside formula, the derivatives are current time derivatives. This is not the derivative with respect to retarded time. This is the derivative with respect to current time. So we need to make use of some of our identities where we related them. And so if we put in some of our identities, we can get this first approximation to our result. So we're going to get nr hat over r hat squared. And then we have a 1 over g here, and we can use that formula which we derived last time, 1 minus 1 over c drr dt. Okay, so this is like Doppler correction factor. And then for the second term over here, we have 1 over c ddt. And I'm going to, since we won't need this anymore, and r hat over r, that's that. The 1 over c came out, and then we have that 1 over g factor. 1 minus 1 over c drr dt plus 1 over c rr ddt RR. Okay, and so because beta is the velocity, so that's where our derivative here, and I took out a c and I have an RR there, and this, sometimes next formula I'm going to replace this by just RR times n caret r. Okay, now if we carry out all these derivatives, and we're going to end up with this formula. This just comes from over here. That's the one term. Then I have the next term. Now we move up to over here. And you see what we've done is we've replaced retarded time derivatives with just regular derivatives. So we got that term there. Now I'm going to get another term from there, minus 1 over c squared. Okay, and now we have two more terms coming from taking the derivative of these two terms. Here I make that substitution that I mentioned there. And this is the final term. Okay, so there's a lot of terms in this formula, but there's cancellations. When we take some of these derivatives, we write it out carefully, there'll be cancellations which will lead to this formula. So the way I approached it and what I suggest here is just start with like the no derivative term. And the only term that doesn't have a derivative is the first one. So we get q over 4 pi epsilon 0 nr over rr squared. And Feynman uses ER with a minus sign for our nr. So this is good. That checks. Okay. Now, let's just work out the terms with a single derivative. And we're going to get q over 4 pi epsilon 0 minus nr hat over cr plus 1 over c d dt nr hat over rr. And now just evaluate that. I'm going to get q over 4 pi epsilon 0 minus nr hat over cr squared drr dt minus nr hat. Now we just use the quotient rule here. Let's see, rr squared drr dt plus 1 over rrc d nr hat dt. And so these two terms are the same. They can be combined and we just get a 2 there. And so it's easy to verify that this is equal to q over 4 pi epsilon 0 rr over c d dt nr hat over rr squared. Because if I take the quotient rule, I have here rr to the minus 2, so I'm going to get minus 2 rr to the minus 3, but then I have an rr here. So I just get minus rr to the minus 2, two terms multiplied by nr hat. So these two come from the denominator here, and then this one rr cancels and we're left with that. So this is the same, and this is exactly equal to what Feynman, again, Feynman is using r prime for r prime for Feynman is retarded, and the c d dt nr same as er prime over r squared. So this is good. So we have verified that for two of them, for no derivatives and single derivatives, are the same. So we got this term, check, and this term, check. Now here's where the cancellations come. So let's do the mixed derivatives. We get q over 4 pi epsilon 0 minus 1 over c squared d dt nr hat over rr times drr dt plus 1 over c squared d dt 1 over rr d dt rr nr hat. Okay, so now we do the same thing, we just actually evaluate these derivatives, and I get q over 4 pi epsilon 0 minus 1 over c squared nr hat d dt 1 over rr drr dt minus 1 over c squared. So that was the denominator. Now we'll do the numerator. C squared rr dnr hat dt drr dt. Now we'll go to this one over here, plus 1 over c squared d dt 1 over rr nr hat drr dt plus 1 over c squared d dt 1 over rr d nr hat dt rr. And you may notice that this term over here cancels this term over here, so we're down to 2 terms, and what's left, these 2 terms are also the same. Because when you take the derivative of this thing, you're going to get an rr squared and minus and an rr squared in the denominator, but that cancels it, so we're just going to get an rr c squared dnr dt dr dt. So these 2 terms are the same, and so from the mixed term we're left with q over 4 pi epsilon 0 minus 2 over c squared rr dnr hat dt drr dt. So this is our result from the mixed term. Now we have one more second derivative term to calculate, and that should give us the final result. So our second derivative term, q over 4 pi epsilon 0. Let me try another pen. Minus 1 over c squared, not much better. nr hat over rr times e2 rr dt2 plus 1 over c squared rr d2 rr dt2 nr hat plus 2 drr dt dnr hat dt plus rr d2 nr hat dt2. Okay. Now, before we do anything, this term over here exactly cancels what we had over here. Okay. And this term over here, put with three things, cancels this term over here. So we're left with, as our final term, q over 4 pi epsilon 0 1 over c squared d2 nr dt2. And this term is this term over here. So it's a long calculation and everything, and how Feynman and Heaviside ended up doing all of this, not knowing that the final answer would be relatively simple. But as I mentioned before, the beauty of this formula is that it's exact. It involves only the charge's motion at the retarded time. Everything here is at the retarded time, except when we're taking time derivatives is at the current time. So what I'm sort of doing is I'm looking at the charge, not where it is now, but where it was. I'm looking at a unit vector pointing to me from there, and then I'm taking derivatives now of that unit vector as the charge moves and the retarded time changes. So this is a very beautiful formula, and the magnetic formula for the magnetic field is just a cross product with the retarded unit vector. So that finishes this series of videos on the Feynman Heaviside formula, and I'll see you back next time for some other topics. Bye-bye.